to Hayden.
Okay. Okay, it's the physics of flight, and it is all about control. You have to push it hard and then it stays off. It's probably more important to see the screen than to see me. In fact, it's a very good idea. Okay, first a little bit of advertising for the STEM project at the Pueblo Weisbrod Air Museum. It turned out that the Air Museum was largely used by pilots to get together and swap lies about the war and so forth, and it didn't have much of a public outreach, and they decided it would be nice to have a little bit of a public outreach, including some educational stuff. So one night some guy showed up here when I was giving a talk to the astronomy club, and they allowed us how they were starting up this education program, and would anybody like to get involved with that. And so Bill and I are part of the whole gang over there. And we have a little thing called a STEM lab. That's science, technology, engineering, and mathematics. In some places they have STEAM. They put arts in there. And for some places, the E stands for economics, which is the dismal science. Here's an aerial view of the Air Museum. In the background, you can see the runways for the airport. And this is out east of town. Go east, young man, and look for a sign. There's the Air Museum. There's the entrance right there. This is an unusual picture because every time I go over there, I see about 10 cars parked around here. It's volunteers working at the Air Museum doing all kinds of fancy stuff. Anyway, we have a new hangar back there, an old hangar here, 60,000 square feet roughly between the two hangars. And the STEM lab is right in there under the wing of the B-29. B-29, in case you youngsters don't know about it, was the kind of plane that was used to deliver nuclear weapons to Japan. It's a high-flying bomber. B stands for Boeing. Okay. Recognize this gang right here? Well, at Family Fun Day, we had some kids from the women's basketball team over there, and they were looking at one little thing here. This light is shining on some highly reflective stuff, and it's explaining about the highly reflective stuff, and you can see that on this gal's shoe right there. And it was just a discussion of how it works. And then right in here, you'll see something which we call the target. It's a bunch of beer cups, soda cups. Standing upside down is a plane on top of it. And right here is a kid. He claps on the side of a carton there. We've got a round hole in it, and we put some smoke in there, and a smoke ring travels across and knocks down those cups. That's a very important thing to learn about, because this kind of turbulence that occurs in that smoke ring there comes off the wings of jet aircraft that are flying pretty fast. And you probably don't recall, but it did happen. Not too long after 9/11, there was a small aircraft that took off from JFK and crashed into an apartment building because it got caught in the vortex of a plane that had taken off previously. It is not a recommended way to come back to ground. Give you an idea what turbulence can be like. This is a wind, in quotes, farm at Vattenfall, which is in Denmark. And the wind is going along there. You got some super saturated air, and in the wake of those blades, you can see sort of what the turbulence looks like. And for wind farms, you typically have to have the spacing between them something like 10 diameters. 15 turns out to be optimal, so that the wake of one doesn't destroy the other one. Also, you've taken energy out of the air, and if you take the energy out, what's it going to do to the next next wind turbine in line? Anyway, we'll get on with planes here. There were a lot of attempts by a lot of people to fly airplanes before the Wright brothers came along, and they all failed. By the way, one time there were some French guys that were quite certain that they knew a lot about flying planes. And they had a sort of a shindig where people would get together and show off their planes, and the Wright brothers went there. And the Wright brothers were able to do all kinds of maneuvers with their airplane, and even the French had to admit that, my God, somebody's better than us. But anyway, they all failed. But now, one rule is that, of course, every airplane that's ever gone up in the air has come down to ground. Not all of them safely. What the Wright brothers understood was the need for control. So, a few preliminaries. This is kind of what we're going to be talking about here. I would have called this Flight 101, except it's kind of pre-college, so it's Flight 099, the 4 forces of flight. A little bit about the center of gravity, and a little bit about the air we fly in. And then we're going to spend a lot of time on the principles of control with some examples, and a note about flight instrumentation. The 4 forces of flight are very simple. The force that pushes you forward, called the thrust, and the force that holds you back, called the drag. Gravity's pulling you down, and you've got some lift, or else you don't get off the ground. So these are in balance at all times when the aircraft is not accelerating. At all times when it's not accelerating. Including when you're descending at 1,000 feet per minute and not knowing it. You can be going down at a steady speed and not know it, or you can be going up at a steady speed and not know it, if you don't have good instruments. Okay, weight needs no explanation. Thrust, we'll be discussing a little bit about that. There are 2 contributors to lift, Bernoulli and dynamic. And there's the drag. So those are the 4 forces. We're not going to talk about the weight, except that in an airplane the idea is that it be as small as possible. And by the way, this plane that you see in the background over here, right in there, that is depending upon its use, a C-47 or DC-3. And in a DC-3 format, it was a passenger plane. In fact, it turned out to be the first one I ever flew on. And back in those days, in order to make flight popular, passenger flight popular, they had gorgeous stewardesses, stewardess, going up and down the aisle serving you something. And in those days, high heels with spike heels were rather fashionable. And the walkway going up and down between the seats there suffered mightily from those spiked heels, because those are really thin, keep the weight down. Okay, now, the thrust always comes from throwing matter to the rear, and it doesn't make any difference what kind of vehicle you're talking about. For example, an old one here is a propeller driven by a piston engine. They usually had radial engines. Instead of, in your car, say you've got a V8 or a V6, the pistons are coming in like this, a straight 6, a straight 4, horizontal opposed 4, a V8, so forth. But this is a bunch of engines that are radial, okay? That way you can get good air cooling on all of the pistons. Another kind is the turboprop, where you have a turbine engine and you have a propeller. Now the turbine engine spins kind of fast. You have a reduction gear here to slow the propeller down relative to the engine, and they're slowing it down in terms of RPM. Exhaust comes out there. It could go out the rear directly. There is a turbofan kind of an engine where you have a turbine engine like this, but instead of having a propeller, you have this big fan in here, and the air is constrained within the cowling and will exit faster, and it's therefore more efficient. And finally, you have the rocket kind of engine. By the way, there's 5 engines right here that are driving this rocket. This one and this one are Roman candles. They use powdered aluminum, and it burns up in the air and provides a tremendous amount of thrust. There are 3 engines on the shuttle itself, which are fed by this tank right in here that has liquid oxygen and liquid hydrogen. But every single one of those things is throwing mass to the rear, and that's how you get your thrust.
Howard?
Yes, sir.
Is there a meaningful distinction between pulling oneself through the air and pushing oneself through the air?
You mean like putting the propeller behind or in front? I mean, that's something that they do.
Like an oar, you know, I mean, I knew, I mean,
Yeah.
pushing yourself through the water, pushing matter out the back of the cellar. Is there a meaningful distinction?
Yes, there is. Because if you're dealing in water, water has a tremendous amount of viscosity, and you get the thrust from taking advantage of that viscosity.
Pushing against it.
You're pushing against it. You're pushing against something that doesn't want to move. And in this case, you're throwing things out at fairly high speed. Okay? And the air itself offers very, very little resistance. Okay, a couple of kinds of lift here. One of them is this Bernoulli lift. You may learn something about Bernoulli's equation if you get that far in your physics comic book. It's about this thick. And I won't write down the equation, but it's an equation. It's nothing more than the conservation of energy for a gas. That's all it amounts to. But there are a couple components to it that matter. One of them is a pressure component, and the other one is a velocity component. And the upshot is that there's a trade-off between airspeed and air pressure. The higher the airspeed, the lower the pressure. The lower the pressure, the lower the airspeed, the higher the pressure. So as a wing goes along like this through the air picks up, goes at higher speed over the top of the wing than it does on the bottom of the wing, and the upshot is that you have higher pressure on the bottom than you do on the top, and that provides lift. And usually in a plane it provides something of the order of 85% of the lift. That depends on this, that, and the other thing. But remember that most of the time the plane is in the air flying kind of straight and level. Okay, the other part of the lift is dependent upon the angle of attack. They're showing a wing here at a small angle, larger angle yet. And the coefficient of lift is something that follows a curve about like that. Well, you'll see a short video about this part right in here. The lift per unit area is equal to some coefficient times what's called the dynamic pressure, which is 1/2 the density times the square of the velocity. Drag is a retarding force when the plane moves through the air, and the drag per unit area is equal to a coefficient of drag times the same dynamic pressure, 1/2 rho v squared. And as a function of the angle of attack, the drag goes up like this and then gets kind of crazy. But anyway, we've seen the lift per unit area and the drag per unit area are very, very similar equations except for the coefficients there. And the lift to drag ratio is equal to the ratio of those two coefficients, the lift coefficient versus the drag coefficient. And so that lift to drag ratio is a matter of design, and not so much the, well, design and the angle of attack, but not so much the velocity. Okay, so here's sort of what the stream flow looks like for about a 6-degree angle of attack, a 15-degree angle of attack, where you reach the stall point and you start beginning to get some turbulence back here on the wing, and at 25 degrees it gets pretty rough. You get crazy turbulence. And here's a little video, and let's see if it works. Okay, showing the varying angle of attack and then what's sort of happening with the wind going over the top of the wing. I didn't make up that video, I stole it. Okay, here are the components of drag. That's the total drag, because you've got the what's called induced drag, which has to do with the angle of attack, and you have form drag that has to do with the shape of the body. Now, and this is a function of airspeed, but what isn't shown here is the pilot. The pilot is doing some stuff. And at low speed, at low airspeed, there's a lot of induced drag simply because he's tipped his wings quite a bit using the flaps. Okay? And as the airspeed increases, the induced drag drops off like this. The form drag is something that goes up with the square of the speed. And anyway, the total drag is in there and has a minimum at some given airspeed. Right now you're probably asking how to measure airspeed. They use what they call pitot tubes. Or if you want to get somebody's nose out of joint, call it a pitot. Those things are hotter than a $2 pistol. They're kept that way because if you're flying at high altitude, you might start condensing some water in there, get some ice, and then you don't know what you're doing. And in fact, there was a video we saw, a Nova video I think it was, where a plane leaving South America someplace got up into some supersaturated air, and it didn't have enough power to keep this pitot tube hot, and they lost knowledge of their speed, and all the automatic controls depended upon knowing that. They died. Curtains. Anyway, you get the dynamic pressure, which is 1/2 the density times v squared, recorded in this thing, and we have a little device over at the STEM lab where we have a leaf blower there, and I built a little pitot tube called a piece of brass tube, and it just looks into the nozzle, and it gives two indications. One of them is it shows the airspeed, and the other one is it goes into a U-tube that has water in it, and what happens is if you go to 125 miles an hour, it does this. You go to 150 miles an hour, it does that. And so that's water, and you can see a height difference in you know, a couple tens of inches of water. So here is the airspeed reckoned in miles per hour, and the dynamic pressure in the centimeters of water. At sea level, you get this. At Pueblo, you get that. 1/2 the density times v squared. And the density here is lower than it is at sea level. Center of gravity. A friend of mine came back from Germany once on a military plane, and he was the only passenger. It was a cargo plane. He was the only passenger. See where it says CG? Sit there. Terribly noisy in the back of that plane. Anyway, the weight here is a little bit forward of the center of lift, and that's the way you want it. There's a very narrow range where you want to have the center of mass, and this goes by the design of the plane. But there was a case where there was an acrobatic pilot that was, you know, flying around. They put a camera underneath it once so they could photograph all this stuff. Well, that camera shifted the center of gravity to behind the center of lift. So he flew up into a stall, and you can't do this because the center of gravity is behind the center of lift. You want it the other way around. Okay? One more of those tragic stories. Anyway, I'll learn a little bit about the atmosphere here. This is a calculation you might learn about in physics sometime. You can calculate the number of molecules per cubic centimeter at sea level, and it turns out to be that horrendous number, written out with zeros, but it's 2.5 by 19. 2.5 times 10 to the 19 molecules per cubic centimeter. You've learned the ideal gas law, PV equals nRT. Put in 1 mole. Okay, you got Avogadro's number, and you can translate that into number of molecules per cubic centimeter. Okay, you come up here to our altitude, and you still have this many molecules per cubic centimeter. If you get up there to the top of Mount Everest, where you can't breathe, look at the number of molecules you've got up there per cubic centimeter. It's rather stupendous. This mechanical pump refers to the mechanical pump that I have over at the STEM lab, which we use for showing various vacuum experiments. And with blank off pressure, meaning just go right to the instrument and clamp it off so no air can get in, you still got that many. The best mechanical pump would do something like this many. The best lab vacuum is something like 10 billion molecules per cubic centimeter. In fact, down at Oak Ridge, there was a guy that built up this fantastic vacuum pump, and he had every kind of pump on this thing in his system, and he pumped to that kind of vacuum. And one day he did an experiment. He opened up the door, took his finger, wiped it on the wall, closed the thing up, and it took him something like 3 or 4 weeks to get to the vacuum he had before. I mean, nature abhors a vacuum. Interplanetary space, we got about 10 per cc. Interstellar space, about 1 per cc. Intergalactic space, about 0.1. But your altimeter reads the atmospheric pressure. That's what tells you your altitude. Except for one little problem. That is, you know that the atmospheric pressure varies a little bit. It's reading 29.92 or something like that. So if you're flying along and you want to know what your altitude is, you got to hear from the local airport or local whatever what the atmospheric pressure is, and you make an adjustment on that, and you'll be then correcting. Then you can read your instrument and get the correct altitude. Both lift and drag decrease as the atmospheric pressure decreases. They both had that 1/2 rho v squared in them. And what that means is if you fly at higher altitude, to get more lift, you have to fly faster. Okay, that's sort of a quasi-logarithmic scale, 1, 10, 100, 1,000 kilometers in altitude. The thing that makes it quasi is the fact that sea level is down here at 0. There is no 0 on a logarithmic scale. If that's 1, then 0.1 ought to be down here, 0.01 down there, 0.001 down there, 0.0001, and so forth. Okay, so it's, anyway, it gives you an idea of altitude. What planes fly typically at around 10 kilometers altitude. Radiosondes go up there. Supersonic planes go up there. Spacecraft satellites are way up there. And there's the top of Mount Everest. And on that scale, Mount Everest is what, 30,000 feet? About that. And Pikes Peak is around 15. 15 is half of well, let's see. So we want to cut about 8.5 down by 2, 4 1/4. Pike's Peak on this semi-logarithmic or crazy logarithmic scale would be about there. Now we're going to talk about control. Control is achieved by feedback. And I'm going to give you an example of a control system involving the human brain. You have a reference standard saying that you're driving your car, and one of the rules is stay in your lane. So that's your reference standard. And then for some reason, the car is a little bit too far to the left. For some reason. Maybe you steered it a little bit, or you aimed it, but it wasn't perfect, and so it got a little bit too far to the left. So what do? You notice it. Your eyes detect the error. And the amount of energy in those few little photons that come off that roadway and tell you that you're off center or eccentric is totally minuscule. But then your brain figures out that something is wrong. It sends a little tiny signal to your hand to steer it, and you steer back. And then the power steering, by the way, is another feedback and control system that's well, follows the same principles, but it's a hydraulic system. Other types of control system, aside from just using the human brain, there are passive things inherent in design. We'll give an example of slanted wings. And then we have some that are active by design, such as in mechanics, the flyball regulation. Electronics uses it all over the place. Hydraulics, your power steering and power brakes are both negative feedback systems, control systems. Now here's a picture that I swiped off the net showing a plane which has stability against roll. Roll is as you're flying that way, this kind of tip like that, okay? And I'm going to give a little bit more exaggerated view because that last picture is not particularly physical. I mean, it doesn't really talk to someone that has taken a class in physics. But anyway, this one, whoops, come on here. There we go. So these are the wings right in here, and you're going along in level flight, and the Bernoulli force is perpendicular to the wings. We call it, we normally talk about lift, but the Bernoulli force is not vertical, it's always perpendicular to the wings, okay? But with level flight, the lift is vertical. You got a vertical lift over here, vertical lift over there. Those two are equal. And then you have equal and opposite inward forces. For those of you who have added up a vector or two in your life. Now, if the plane is rolled a little bit, tipped, the Bernoulli force is still perpendicular to the wings. But in this case, the Bernoulli force is directly vertical. Here it is slanted, and the lifting force, the component of that's vertical, is smaller. And because this one is bigger than that one, it tends to tip it backwards, okay? And there is some side slip that goes along with that. So this little business of having the wings not be like this, but be like that, is a control thing that keeps you from rolling. Okay, aspects of control. The plane is tipped, you get some feedback, difference in the lift forces, the correction, the force difference tips the plane back toward level flight, and well, I forgot, there's one more thing, forget it. Okay, the other part was you want something to damp out the oscillation so that the plane doesn't do this. It could oscillate because you're always forcing it back to the center. We have a name for that. It's called simple harmonic motion. Put a ball on a spring, it just oscillates, right? That's because of restoring force directly proportional to the distance away, and it just oscillates. So you have to have something in there to damp it. Well, if you got a wing from here to the wall that's this wide, moving through the air like that, that does plenty of damping for you. Okay, now we're going to talk about active controls. And the prototypical thing was James Watt's RPM controller for steam engines. I wrote about this once, and a friend of mine in Connecticut told me that I was wrong because I attributed this whole system, this whole design thing, to James Watt. And he said, no, that isn't right. This kind of system was used for controlling water flow in overshot mills, overshot wheels in water mills and so forth, long before that. And if you ever get up to Royal Gorge, you get up the Royal Gorge, you go in there, you'll see a clock that runs by water. And if you look up there at the top, you'll see some of these spinning balls, and they are what actually control the clock rate. Now the idea works like this. This part right in here, this whole shaft rotates, and it's driven by the engine. The faster the engine goes, the faster this thing goes. If you are going, if you're going too slowly, these balls are you know, instead of hanging like this, they hang like this. And when they come down a little bit like that, they push this down, pushes down on this lever on this side, lifts it up on that side, allows more steam to go into the engine. If you're going too fast, they swing out. When they swing out, they lift this up, and then this end of this lever lifts up, that end goes down, and it cuts off the steam. You ever looked at your lawnmower? You pull a thing to adjust the speed, okay, but you're only saying how fast it can go, so to speak, or you're adjusting sort of the fuel flow. But there is a little device in there, a flapper, that responds to the airflow off that fan on the top. And if your engine starts to turn too fast, that thing comes up like this, and a spring assembly slows down, or you know, sort of shuts the throttle down a little bit so you don't get as much air and fuel in there. Okay, it's a negative feedback system, and the upshot is that faster begets slower, slower begets faster, but there is always a return toward the reference standard that we have put in. So for automatic stability, you got to have a well-defined standard of reference. What is your standard of reference? Going down the middle of the road, for example, right over the yellow stripe, whatever. For some reason, explained or unexplained, explained or unexplained, there's a perturbation, some deviation from your standard of reference. A sensor detects that. A sensor sends a signal to cause a restoring force back toward equilibrium. And then, of course, you have to have an energy dissipating mechanism to keep it from overshooting. Now, about that reference. We're going to talk a little bit about some instrumentation, and then, who's got the tomato concession? I've got two instruments out of planes right here. This one here is a device that in principle can tell you if your plane is, I mean, it's sitting in the dashboard like that, and it can tell you if you are tipped downward or tipped upward. This is sort of an artificial horizon here. And it can also tell you if you're tipped this way or tipped that way, because you might have flaps that change your orientation and so forth. This depends on a gyroscope. I'll pass it around, you can look at it. The gyroscope isn't turning, so that thing looks just kind of crazy. This one here is a gyroscopic compass. On the top it says fore and aft. There's an arrow, so that is sitting with this arrow pointing forward. Got a few places to hook up some wires right here. And it runs a gyroscope. And if you look at this thing, you can see a gyroscope that's in there. And you can see that it looks, let us say, a little bit more complicated than that gyroscope right there. So I'll pass this around. $5,000.
If I break it?
Yeah. Okay, so we're going to talk about gyroscopes here, just a little. First, a little bit of vocabulary. We have yaw, pitch, and roll. These are three different kinds of rotation. A yaw is the kind of turn you make with your car if you're going north and you turn east. That's a yaw rotation. The pitch rotation is going up or going down with the nose, and a roll is the wings tipping up or down like that. By the way, that stuff we're talking about is extremely important, and it'll be on the next exam. Okay. The device, the little instrument that I passed around that's over there, is a pitch and roll corrector, and this one over here has a gyro that's for yaw. And the way it works is the gyroscope likes to maintain its axis in a constant direction. The instrument case tips, as I did, and the gyro keeps pointing in the same direction it says here. But how do we guarantee that? Now I need a victim here. Just a minute here. Young lady. Now I want to see if you can do something that's very hard to do. Grab a hold of this like this and tip that, okay?
Okay.
Just do that. Easy, easy. Okay, do not leave.
Okay.
Please repeat. Something isn't quite the same, is it?
No.
Well, in fact, it's really quite a bit different. So we're going to discuss a little bit about gyroscopes here. I'm not going to tell you how they work. Yeah, so you got a standing O or something here. I'm going to plug in this gyroscope here, and let's see, is it? Let's see here. Okay, oh. Are we turning now? Yes, we're turning now. This thing doesn't grab and turn very well. Okay, there's a gyroscope spinning around an axis like that. And what's going to happen here? You got this gyroscope spinning around that axis like that. And watch what happens when I put this weight on over here. This is called precession. If it does this kind of thing, it's called nutation. But what you'll notice is that the end of that axle is going down like that. And the reason that's going down is because of friction in some of these bearings, like this one and so forth. In fact, in Connecticut we had about 10 of these things we used and for student labs, and every semester before we used them, or every other semester, one of our guys would take them apart and use an ultrasonic cleaner to clean up all the bearings and so forth. Okay, now what I want to do is show you what happens when I am going to make a turn here, and let's see here. I think I want to go to the next page here. That thing there is a picture, sort of this particular device. So we're going to pretend that the plane is going to do a clockwise rotation. Carefully observe. Okay, get this out of the way like that. Now, if I'm going to do a clockwise rotation, which I'm going to be pushing on, it's clockwise from the top. Okay, some of you youngsters got to learn. There's clockwise, counterclockwise, and digital clockwise. This clockwise. Now watch what happens. If I'm going to rotate this thing like this, the nose takes a dive. If I rotate it like this, it goes the other way. Now, think of this whole system right here as being that device right there sitting in an airplane. It's sitting in an airplane. It's got this gyroscope in it, and you do some rotation like this in the airplane. Now there is a little bit of drag when you do that, a little bit of drag, and as you drag it like that, then there is, what you're doing is pushing right over here, and you're causing the end of this axle to take a nosedive. Right? All right. So the friction in that particular bearing that's right down here is causing the end of this axle to tip downward. Now the idea is to sense that tip downward. So you have sitting in here, and actually in that gyroscope over there, these bearings right here would be out here, but you have a sensor that detects that force. So it exerts, when it tips like this, or goes like this, it exerts a downward force on that bearing, an upward force on this bearing over here. And so what you want to have is a sensor that picks that up. So you have some kind of a sensor that will detect this downward force over here, this upward force over there, and then what to do? You're going to send a signal, say, I want to correct this. What am I going to do? You have to go back to what's causing the problem. The thing that's causing the problem is the friction in this bearing, which is actually not so bad right now, but you know, over a period of hours and hours, that's going to go bad on you. Okay? Now, as that thing spins around, my God, we don't want a plane to spin like that, but it's going to cause that nose to tip. So what we want to do is have a motor and that will do something for us. That is, as we go like this, there's a tendency for the nose to go down. We detect a force over there on that side, and then what we want to do is to have our motor turn this gimbal back. Okay? Because the problem is the friction in that bearing, and we want to counter the friction in that bearing. Put in an equal and opposite torque on this bearing right here by using a motor. Okay, so the motor would actually then, as this turns around causing that nose to go down, the motor would be over here and the motor is a connection between the plane and this gimbal right here, and it would tend to rotate it back until there's no force. You could detect the force up or down on either axis or something like that. So as the plane flies and makes a rotation like this automatic control system, remember I showed you all those connections in there, what that thing does is it turns a motor that's inside there that counteracts that friction in the bearings. Okay, and brings that thing back to exact straight. The guy that cleaned the bearings on this thing was a submariner or a submariner, choose your pick. One under the North Pole. Their gyro went berserk. One of them did. You don't depend on just one. Okay. Next thing is the idea is there that the plane can rotate without changing the direction of the gyroscope. So that gyroscope remains your standard of reference. I'm going to talk about another kind of gyro because these gyros are now in a lot of our big aircraft. It's called an optical gyro. The principle of it was discovered by Sagnac back in 1913. But the upshot of it is that you have a long coil, and I'm talking about kilometers of fiber optics going around in a circle. Okay? And you have two ends of that fiber optic thing, and what you do is you send some light from, well, it's easier to think of it as a light pulse. Send the light pulse in both ends, and the light goes clockwise and counterclockwise around this loop. And it takes the same length of time to go around unless the whole system is rotating. And if the system is rotating, you have a different light speed relative to your position in that system. Counterclockwise and clockwise, you pick up the difference between the two, and that tells you how fast you're rotating. It doesn't tell you direction, it only tells you how fast you're rotating. So anyway, what you do then is you measure the rotation rate, and then you say, well, how long did it rotate, how fast, and so forth, and you integrate to find out how far or what your orientation is relative to your starting orientation. So there's a calculation that's involved, and that makes it different from this that keeps the same orientation. And it also, by the way, must be corrected for the rotation of the Earth of 360 degrees in 24 hours. But we call that arithmetic. It's kind of no big deal. Okay, the take-home message about control is you got to have a standard of reference. You have to be able to detect the deviation from the reference. You provide negative feedback, that's also called corrective feedback, to drive it back to the reference condition. Back to the basic physics here. The lift is caused by speed, not by power. And you might learn the Bernoulli equation in your physics class. Get ready. The thrust is caused by throwing matter to the rear. You'll learn a little bit about that. Something like F equals the derivative of the momentum. And the drag is caused by the shape, the angle of attack, and the speed. The equations are for experts. I mean, go design a wing. You know, there's still arguments about the best wing design and so forth. The propeller designed by the Wright brothers has been improved upon by about 10%. Okay, know thy instruments. You have to know your altitude, your speed, your location, direction, local air pressure, temperature, winds, all that kind of stuff. You can fly by the seat of your pants only in clear weather in still air. The rest you really ought to have instruments. Control always depends on a standard of reference, and your nerve endings can deceive you. You've got to have a reliable standard of reference. And before flying, you should use a blue flight card. This was what a friend of mine had who was a pilot when I was in grad school. A little card in your pocket. It's blue. It has 2 holes in it. Hold it up to the sky and look through it. If the color of the sky does not match the color of the card, don't file a flight plan, don't leave the ground. That's for small pilots and so forth. So I think that's probably the end of it. So there you go. Questions?
Questions?
Shoot.
So the control system, it sends messages to some control surfaces. Right?
Yeah.
Okay. So there's a model in there, but what activation of those control surfaces, I assume, right, is going to cause the plane to do somehow.
Oh, yeah.
Right? So because otherwise, you could give a signal and you could do the wrong thing, right? So it's somehow. So that model. So how wide of a range of positions or flight regimes is that model based on? Is that understandable? So like if the plane gets into some really strange position that you wouldn't have anticipated, does the control system still kind of know what to do?
Well, can I say that depends?
Sure.
Without being, I don't want to be accused of being a lawyer, but it depends. If you're talking about a commercial passenger aircraft or transport aircraft or something like that, they are built to have fantastic stability. If you're talking about a jet fighter plane, they are deliberately built to be unstable, because they might be flying along like this, and then all of a sudden they want to go that way. That works best if it's unstable, because a deviation from straight forward gets bigger and bigger as you go, as you get farther and farther away from the straightforward orientation and so forth. And so in those aircraft, they have just a phenomenal number of sensors and correctors and so forth, because they have to fight actively. They have to fight to maintain stability against the inherent instability of the airplane itself. So
if you get too far out of that regime,
you
end up just crashing out because you can't control it.
Yeah.
Control system.
Except in the jet fighters, man, they have got an extremely wide range that they can correct from, because they're
modeling a whole lot.
They're modeling a whole lot, yeah. You betcha. But for a passenger to fly your kids in from Bora Bora or something like that, you want it to be really quite stable. Yeah. Bill.
So what happens if your plane does stall and you lose all control, besides praying or something? What do you do to regain control?
In some cases you can't, but if the the way you get into a stall is by flying up too steeply usually. And if the center of weight is forward of the center of lift, you can just flip your flaps a little bit, and you'll dive down and pick up speed, and you'll gain control. If the center of gravity is behind the center of lift, you crash. Yeah.
I've seen these pictures of these aerobatics where they fly straight up.
Yeah.
And they go to zero velocity for a second and then start falling down backwards again, tail first.
Yeah, but they have got they can regain control of those things with flaps and all that kind of stuff. By the way, speaking of such things as air shows where you see these things, Don Blem actually was recorded one on a home video once. He was at one of these air shows, and there was a plane that came swooping in there real fast and so forth down near ground level, and the tower was telling the pilots on the ground to quick, get your planes, get right in behind him. I mean, he saw the plane overturning, yeah.
Yeah, actually, I was interested, I don't really know much about this, but do you know anything about the vectors thrusting the nozzle
The answer to the question is no. No, I don't know. I don't know anything about it at all. Thanks. I'm not a pilot, and so when I fly a plane, it's sitting in a seat number 2250 F or something like that. So, oh, I saw a picture of the, what is it, the new, is the 787, the Boeing, that really fancy one's got a problem, the Dreamliner. Saw a picture of that, and it said it was for sale, batteries not included. So, okay.
You said every airplane that has ever gone up has come down?
Yeah.
Does that include all the airplanes that were lost in the Bermuda Triangle?
Ooh. Good question there. So, okay, well, I've told you everything I know and more.